Hello, my name is Geil, and I am a grad student in mechanical engineering at the Global Engineering and Research, or Geil Center at MIT. And today, whenever you're watching this video, you will hear about the fatigue analysis of low-cost, high-performance, mass-manufacturable prosthetic feet for low and middle-income country markets. The authors would like to declare that there is no conflict of interest. So just to quickly go through what I'll describe during this presentation, I'll work backwards through my title, which is, I know, kind of wordy. First, I'll describe unmet needs for prosthetic feet in low and middle income country, or LMIC, markets. Second, I'll discuss the design of low-cost, high-performance, mass-manufacturable prosthetic feet, or the work that has been going on in Geil Center over the past 10 years or so. And here is a picture of our current prototype. And lastly, I'll go through the fatigue analysis of this current prototype and how we made some design decisions moving forward. There is a major unmet need for low-cost and high-performance feet. There are over 40 million lower leg amputees worldwide, and 80% of transtibial amputees live in LMICs, or low and middle income countries. There are greater than 1 million lower leg amputees in India alone. Amputees require different prosthetic feet based on their activity level. In LMICs, most amputations are caused by trauma, so these higher activity amputees are better suited to energy storage and return prostheses. However, carbon fiber ESR feet and active feet are prohibitively expensive, as demonstrated by this cost-performance curve, and conventionally available feet are heavy, damping, and do not meet international standards like ISO 10328. As a result, many amputees in low and middle income countries, LMICs, use prostheses with poor performance for their specific mobility needs. Using poorly suited feet is problematic for joint health, but also specifically for amputees in LMICs who face personal and societal consequences for appearing disabled. This means there is an unmet need in the market for low-cost, high-performance ESR feet. Prosthetics work in the Geil Center aims to create ESR, energy storage and return performance, at the cost of conventional prosthetic feet. So that's the goal for the MIT Geil foot. The lower leg trajectory error, or LLTE, framework predictively designs prosthetic feet to mimic able-bodied walking. The LLTE metric is the error between predicted gait and able-bodied reference walking, as demonstrated by this video here. We have the reference data set in the dashed line and our predicted gait in the prosthetic foot, followed by the black line. Now, the design objective of minimizing LLTE designs feet that reproduce able-bodied gait by optimizing the geometry and stiffness of those prosthetic foot designs. Early prototypes performed as well or better than commercial carbon fiber ESR feet in gait lab testing, and they proved durable through extended field trials in India in 2023. Now, recently, these prototypes were redesigned to facilitate mass manufacturing, address user feedback, and meet international standard ISO 10328. Specific design changes include incorporating C-channels for injection molding, splitting the keel for lateral stability, introducing a sandal toe to accommodate thong sandal shoes, and sculpting the ankle to appear more biological. Now that we have a mass manufacturable design, we can address prosthesis lifetime to head toward a commercial product. The aim of this study is to analyze the trade-off between biomechanical walking performance and predicted fatigue life of a prosthetic foot in order to select a final design that meets international standards and maximizes walking performance. So next I'll go through the methods for this study. 5 prosthetic feet with varying endurance limit safety factors were optimized using the LLTE framework. Here's what these 5 feet look like. The independent variable that we changed was the safety factor for each foot, or effectively, the max allowable stress for each run of the optimization, or the max allowable stress in each design. Here are the safety factors for each foot. So a high safety factor means a low max allowable stress in the foot. This creates a stiffer foot, which leads to a longer fatigue life, but also worsens walking performance. This is reflected in the high LLTE value. Conversely, a low safety factor indicates a high max allowable stress, yielding a softer foot with a low LLTE or less deviation from able-bodied gait. Here's the low LLTE value for sample A. and the LLTE values for the other 3 samples. Quick caveat is that users prefer LLTE to be below 0.14 according to previous sensitivity studies. So the answer, or the question this study is hoping to answer, is how much performance must be sacrificed in order to meet the ISO 10328 international standard. Each foot was encased in the same polyurethane overmold with a rubber sole and underwent ISO 10328 fatigue testing to 2 million cycles. A universal testing machine was used to measure the stiffness profile of unused and tested feet via the AOPA test, and deformation was measured at the forefoot, heel, and ankle. We also took measurements on both the overmolded feet and the keels using CT scanning. So overmolded feet were measured using a digital height gauge pictured in the back of this image and a digital level, and measurements were taken 5 times at each location. Tested and unused feet were CT scanned to assess internal deformation. Scans of the keel were aligned at the midfoot, and displacement fields were generated using Voyager. So here are the results. All samples sustained 2 million cycles, which is very exciting, but there was minor plastic deformation. Here are the results from the deformation. One thing to note is that measuring on the overmolded feet was difficult since they were no longer flat on the bottom. The fact that both the overmold and the keel measurements differ tells us that the keel and foam are both deforming. I'd like to point out that sample C deformed the most across the board, and this is surprising, and we hypothesize that it's because of a stress concentration due to C-channel rib placement, since ribs are added manually as a post-processing step. Sample E, which is the stiffest and the far right bar in each graph, predictably deforms the least in all trials, except for the forefoot overmold condition. We hypothesize that the foam is what deformed in that case, as it is squished by the stiff keel. Here are the results from AOPA testing. You can see from this image that we achieved a dynamic keel, but we still have a cushioned heel. The heel stiffness increased about 3.5% on average, and forefoot stiffness increased by about 2% for small displacements and about 35% for large displacements. So now to move on to the discussion and conclusion. Foot A was selected to move forward in our research, or to move forward towards the goal of a commercial product. The LLTE value for this new foot is, I got ahead of myself. This foot is ISO 10328 compliant, so it sustained 2 million cycles. And also it has an LLTE value of about 0.12, which we know from previous sensitivity studies is acceptable, to users at least. We also know that it has an AOPA dynamic keel and cushion heel. Based on these results, the fatigue and performance trade-off, sample A was also selected for further fatigue testing. So it sustained 4 million cycles, and we're still working to process that data. And this sample is undergoing ongoing field testing in India right now. Thank you so much for watching this video, and I hope you learned something new.